Hey guys, good morning, good afternoon, good evening, wherever you are on the planet. I'm Mike Aubrey, and then today, as always, the wonderful Princess Aaliyah Pandolfi. We're here uh, bringing you the next kind of webinar series in the UAV Challenge. Also, we have Scott Williams with us, one of our regulars within the challenge. Hey, Scott, and then our
And
special
actually, our South
and
African director.
well, details. Sorry, man. um, now that I'm good and red-faced for all you guys over the webcam, let me introduce who the star of today's webcast is. Rich Fletcher. Thanks for being here. Rich is with the Massachusetts Institute of Technology, and for those of you that if you're familiar with MIT, they're basically one of the premier research facilities really on the planet. He works in what's called the design the MIT Media Lab there, which is an entire facility basically dedicated to the advancement of up-and-coming technology. So he's what you'd call a power player in the world of technology. But he's also done a lot with RFID tags, and so I know this is a subject that all of us have been interested in about kind of ways to work around with it and stuff. And so that's actually the focus of his presentation day. For the background of him, he's done a ton of field work out there in developing countries. He's Colombian natively, but I'll let him give his own introduction. So, Rich, thank you so much for being here. We're all really excited to learn from you today, and I'll give
Sure.
the form over to you guys, or to you, sir. Thank
Okay.
you.
Yeah. Um, yeah. Thanks for the opportunity to chat. I think this is a interesting project and a great cause. I was just gonna give a general overview to RF and RFID. So I'm assuming very little knowledge of RFID just to start with, and
It'll vary.
there'll
Yeah.
be okay.
Yeah.
There'll be sections where we can pause and maybe take some chat questions or something like that.
Absolutely.
Yeah.
Sounds
Okay.
awesome.
Yeah. So, uh, yes, as Mike mentioned, I did my undergrad and grad school at MIT, and I currently work there both at the Media Lab and also at a place called D Lab. And D Lab is focused on technology for developing countries. So I do a lot of work in India, and D Lab itself does a lot of projects in Africa. Although I personally don't work in Africa currently, but yeah, we work all over the world. And about 10 years ago, when I got my PhD, I also started a company called TagSense, just me and a few other people, and we do a lot of projects for all different kinds of companies, just building custom RFID systems, things that you can't find off the shelf. But we also sell a few items as just as stock items on our website. So that's what TagSense is. Okay, so we'll get started. Can everybody hear the screen or see the screen and hear
Yeah,
okay?
we can. I can see you just fine.
Yeah, okay. All right, so first I'll start off with describing passive RFID. Um, and RFID basically requires you have a transmitter and a receiver. So some of you may be familiar with RFID as like a card to get into doors or maybe to get into a parking lot or get into a building. But essentially, you have you have a signal that goes through the air, then it has to go through some, it might have to go through some materials, and then it goes through air again to a receiver. I'll talk more about this later. But the way RFID, passive RFID generally works is the tag has no batteries on it. So if any of you use a RFID, for example, as a train, to get on the train or to get on the bus, it's generally you're probably familiar with something that looks like a card. So that card is basically has a chip and an antenna, but that's it. There's no battery. So the power actually comes from the reader, and some of the energy is scattered off of the tag, and then the tag that powers up, it powers up the chip, and it modulates that energy, that backscatter, and that's what you see as data. So all RFID tags, even though the how the radio waves go back and forth are different, the general principle is the same. So basically, you have some kind of signal, a way of getting that signal to the reader, and you have a way of modulating that signal. So a very simple example is I don't know if anybody does this anymore, but you you may be familiar with like smoke signals. So you can start a fire, and somebody far away can see that fire, and then you can use like a blanket or something to modulate that fire, to send the fire up in little bursts or puffs of smoke, and that's how you can signal and send data. So this is similar thing. So you have some kind of RF signal, and all the tag does, it's modulating that signal. So here's a picture of some typical low-frequency RFID tags that you might use for either animals or for cards to get into a building, for example. Readers come in all different shapes and sizes. Some are very large that are used, for example, on trains, and some like for tracking train cars or trucks or a shipping yard, and others are much smaller. I won't go too much into detail here, but basically those of you who might have a engineering background, you know that if you have an inductor and a capacitor together, it forms a resonance. So that's a signal that we use, and then the chip on the tag just simply detunes that resonance, and that's what we see as data on RFID. There's something called semi-passive, which means that there's a battery built into the tag, and that helps extend the range so that the tag doesn't need to get all of its energy from the reader. So the raw signals look like general, mostly like sine waves, and then there's different ways of encoding data, which I won't get into detail, but there's, as you know from those of you who study radio, there's different kinds of modulation like AM, FM, etc. But generally, the tag uses AM modulation to get you a first level of modulation, but then there's an additional modulation on top of that, which could be based on frequency or other types of modulation, like phase shift keying, for example. Okay, so in the far field, and these are tags that are increasingly being used by stores, for example, like Walmart here in the U.S., to tag items such as, I don't know, clothing, for example, on the shelf. So you might have a handheld reader and go down the shelf and do your inventory. It's also, used in some places for library books. But so the far field RFID is also passive, but far field indicates that we're using the generally higher frequencies, and we're using the component of the electromagnetic field that actually radiates. So you can make a directional antenna and send out a beam of energy that hits the tag and bounces off of the tag, and then, as I mentioned before, the tag modulates it so you get some data back. One simple example that is common here in the U.S. is the automatic toll collection. So you might have a tag in your car, so as you go through the toll booth, there's an antenna, overhead in the toll booth that sends a beam of energy down to your tag. It energizes it up, and then your tag scatters the energy back with some data. And then once again, you can also add a battery to extend the lifetime, or sorry, extend the range of the tag. And here's a picture of a semi-passive tag that we built in the past. So you can build it out of discrete components, or you can nowadays you can just get all this on a single chip in a very thin, cheap label, and it's amazing how much the price has come down over the last 10 years. But far field UHF RFID tags that are used in high volume are typically on the order of 10 cents. But if you wanted to buy a sticker in lower volume, you probably would pay something like maybe 50 cents. But it's quite cheap. Let me now move on to active RFID. So I just described passive RFID. I don't know if we should pause there. Or are there any questions just on passive RFID?
I do.
Yes?
I have a question.
Yeah, there are questions. Go ahead. Go ahead.
Okay.
Oh, wait, Mike, are you going to wait until the end to ask all the questions, or did you want to
Well,
do
I
it
think
in sections?
it depends. I think right now there's really only one. I think kind of generally, yes, we should shoot to do that.
Okay.
I have a question
This,
on on the passive ones. What's the range of the passive ones, Rich?
Sure. Yeah, that's a good question. In general, we can detect an RF signal very far away, as you know from, for example, your cell phone. Like in the U.S., you can detect the cell phone tower can talk to your phone from miles away even. However, with passive RFID, because the tag is being powered by the reader, the signal and the powering limits your range. So typical range for a backscatter tag, for example, it goes as 1 over the distance to the fourth, so to the fourth power. So your distance for low frequency RFID, your distance is roughly limited to the diameter of your antenna and the size of your tag, and it generally goes as the ratio of the tag diameter divided by the reader diameter cubed, so to the third power. So for example, if you make the tag twice as small, the read range goes down 8 times, or the signal goes down 8 times. In a high frequency tag, the distances that you typically get based on the FCC power, and of course, if you didn't have any limitation, you can blast as much power as you want, and you can read the tag at a much longer distance. However, for safety reasons, the FCC limits the radiation in the U.S. to essentially 4 watts radiated power, and in Europe it's 1 watt, and the reading distance is roughly 8 meters is a typical reading distance for UHF passive RFID.
Thanks, Rich.
Okay, so if that's okay, I'll move on to the next section, which is active RFID, which is what we're planning to use for the challenge. Okay. All right. So active RFID is essentially a radio, and it's battery powered. So there's a transmitter and receiver, and both the transmitter and receiver are very similar. Because it's battery powered, you're not blasting a huge amount of energy to try to power the tag on the other end. And in terms of frequencies, the most common frequency has emerged over the last 10 years is essentially the Wi-Fi band, so 2.45 gigahertz band. Traditionally, other frequencies that have been popular are something in the upper UHF range. However, there is no, because cell phone frequencies or cell phone transmissions occur on different parts of the spectrum depending on which part of the world you live in. It's much simpler to just use 2.45 gigahertz because that works pretty much worldwide. So you can use that Wi-Fi frequency worldwide. Even though I say 2.45, it's actually a band of frequencies, and Wi-Fi uses certain channels within that band, and these active RFID tags use other sets of channels, and Bluetooth also uses another set of channels. So they're not necessarily stepping on each other, but that's a popular open band, and at that frequency, the advantages are that it lets you make a fairly small antenna. However, the disadvantage is that these frequencies don't go through liquids and solids very well. So for example, if you have a Wi-Fi card or Wi-Fi antenna, if you cover it with your hand, it'll block the signal. So there is a limitation there. However, because the wavelength is small, the signal is able to leak out and bounce around pretty well. So indoors as well as outdoors, this frequency works pretty well. You can actually put a tag into a metal file cabinet, and even though it can't go through the metal, just the little slits around the file cabinet drawers are enough to let the signal come out. So it is able to propagate pretty well. The tag looks like this, at least the low power one, and the typical range is 40 to 200 meters, depending on how how big of an antenna you use on the reader side. The power is roughly 1 milliwatt, and you can vary the power by sending different commands. You can lower it below 1 milliwatt if you want to. And the data is limited to about 250 kilobits per second. So it's not as fast as, let's say, Bluetooth, but it's perfectly fine for sending data packets. Sending like a packet of data, every few seconds or so. And then we have a variety of readers that can plug into your USB port on your computer. We have another one that's Ethernet. Some people want a handheld. So there's lots of different ways to connect the reader to a computer or to another circuit board, but it's essentially the same chipset. I don't know if there's any questions on that. Okay. I'm going to move on to antennas.
Yeah, I'm not seeing any specific ones. There's questions around updates on FLIR cameras. Yeah, nothing on RFIDs. Guys, if you have questions, I mean, I know that we've had a couple webinars now where the RFID tag has come in. If you know that you're going to have a question here coming up, send it our way so we can put it in the queue.
Okay.
So, yeah, right now we're good.
Okay. All right. So we'll move on with antennas. So there's many different antennas that are all kinds of designs that exist for different applications. An antenna basically takes the radio energy that's on the circuit board and matches it to air. So it lets you transition that energy to air with as little loss as possible. And there's many different designs. Here's some popular ones. So the monopole on the upper left is what you might see like on a police car or walkie-talkie. The lower left is called the Yagi antenna, and that's generally used for television reception, and it also is very directional. So you can move it around and point it, and that's generally used for direction finding. So if you tagged an animal and you're trying to find the animal, in a park, often they use a Yagi antenna that you carry around. Then in the middle you see a dish antenna, and that forms a beam that's used to, for example, to go from one building to another, or even go to a satellite. And probably one of the most common types of antennas is the patch antenna that you see on the right here. Those you can find, for example, in your phone. There might be some GPS antennas those are nice because they're very small and compact. But the basic antenna that you learn, in engineering class is basically a monopole, which is just a single wire, a single radiating element, and the energy goes sideways. So if the antenna is pointing straight up, the signal is propagating out sideways. And then you can also make a dipole, which has a little bit more signal strength, more gain. Some of the antenna parameters that you might see if you go to buy an antenna, or if you're shopping around for antennas, you might see, for example, these terms used: aperture, gain, efficiency, bandwidth, polarization. So I could just mention these briefly. So an aperture is essentially how big the capture area is for the antenna. So the antenna has both a near field and a far field. As I mentioned, the far field is the part that radiates, and the near field is the part that stays inside. So how big that near field to far field transition is called the aperture. But you can generally just think of it as the aperture is more or less the size of the antenna. How big the antenna looks from a distance, from the point of view of radio waves. Something that's very important is you should know that antennas have a radiation pattern, and that radiation pattern is not uniform. So a very common misunderstanding of antennas is, about every month I get a phone call from somebody wanting to buy an RFID system to put on items that that might get lost. So for example, they would say, oh, it'd be great if I can tag my keys and my cell phone, so if I'm more than like 10 feet away, you know, an alarm will go off and tell, you know, so that I know that I left them behind. So the problem with that is that it's very difficult to make an antenna that's what's called isotropic, that radiates equally in all directions. And in fact, it's physically impossible to make a perfectly isotropic antenna, but you could come close. But most of the antennas that you buy or that you use have a direction to them, and it's important that you know which way the electromagnetic field is propagating. And here on this slide, we're showing a patch antenna, which has roughly a 60-degree beam. And as you can see, we're looking at the patch antenna from the edge. So for example, this view can be looking down on a patch antenna that's pointing horizontally, you know, along the ground. So you can see that in the front direction, we get approximately a 60-degree beam that covers a pretty wide area. But towards the back side of the antenna, the gain is rather short. So this is directional. And you could this is just one example, but you could make antennas that are very directional. Like for example, you might be familiar with a policeman who uses a radar speed gun. So the policeman will point an antenna at the cars on a highway to see how fast you're going, for example, using the Doppler radar gun. Those antennas are typically a helical antenna, and they have very high gain, so it's a very narrow, pointed beam. So that's one example. But a patch antenna, a single patch, is fairly wide. You can add more patches and make an array if you want to make it very directional. Then there's other parameters, such as directivity tells you sort of how uniform the radiation pattern is, and then gain. Gain is you can imagine that if I have a very narrow beam, then along that beam I'm going to get a very strong signal. So there's actually you could think of it as an amplification, like the antenna is focusing or concentrating the radio energy in a particular direction. So that's called a gain. And a lot of these parameters are measured in logarithmic units. The other thing you should know, and you know, this may be non-intuitive, but there's something called polarization, which just means that when the radio wave is traveling, it actually has a direction. So it's oscillating, but if you look at the cross section of the direction. So for example, if a radio wave is coming towards you, if you were able to visually see the electric field, for example, it would look like one of these diagrams on the bottom, where the electric field vector could be rotating, or it could be linear, or it could be some combination which gives you an elliptical pattern. But the main point here is that you should be aware of what the polarization of your antenna is, so that you make sure that you can pick up the signal that you're trying to pick up. So some of the common antenna types are here, as I mentioned before: monopole, dipole, patch. There's a microwave horn, which is metal, and then there's a helical antenna, like the type that the police use, for example. So let me pause there. Are there questions on antennas?
Take myself off mute here. Yeah, there are a couple.
Okay.
And actually, they have to do more specifically with the challenge. So actually, Scott, these might actually be better directed at you or for our side of things. Questions around the specific frequency that we're using in our competition. Do we know if we're using 2.4 gigahertz for our frequency? Is that, yep, all right, that's one. And then on the rhinos themselves have RFID tags on them. Where are they generally situated on the rhino, and are there best practices for tracking them from an aerial perspective? I'm gonna buy you a microphone. I'm gonna pick it up. I'm gonna send it. I'm gonna airmail it to you.
Unmuting him. How about unmuting him? That would help, I think. LB, I think
Oh,
you're gonna
is it
have to
us?
unmute from your
Oh, it's
side.
our end. Okay, I think it's on your side,
Yeah,
man.
now it's on your
Uh,
side, LB.
yeah.
Now I'm good. Okay, cool.
There
Yeah.
we are.
So
Hey.
good, awesome. No, normally what you will see for a rhino is a bracelet, typically on their back ankle. Not that it makes a big difference. And for the most part, you know, the VHF trackers that you see these days, as far as I'm concerned, are useless. But that's my own opinion. Going out there with a big antenna and trying to track them around and listening to beeps and squeaks doesn't work very well. So RFID tagging is a completely new thing, and it's something that we're very deep into on the RPA side. But the old literally putting a VHF tracker on there and you can do DF to try to find them is very, very hard to do and ineffective at best. I guess the big answer is for now it's bracelets until the battery power is to a point where you can fit it into a horn or something like that. It's probably going to stay as a bracelet. Rhinos have strong wrists, so you can actually airlift them by their wrists, oddly enough.
Wow. So, I bet that's quite a sight to see. So what, you turn them over and you lift them up?
Is you should yeah, you actually should go Google it. It's pretty cool. So
okay.
you can literally wrap around their wrists and pick them up while they're under anesthesia. Obviously, that's actually the safest way to transport them. So.
Oh wow.
But yeah, so for now they're bracelets. You can imagine that kicking a bracelet on a rock we've had one black rhino that would never let his bracelet last longer than an hour. He would break it. So we're looking at a lot of different places like the ear where it stays clean. But I think you'll probably see that when you come down in November.
Okay. Thanks. Rich, I think this question is good for you. I'll just read it directly. It's from Michael Robbins. Could you please explain DBI gain? Is this an actual amplification or is it just an indication?
The DBI gain is so let me see. I think I have a slide for that.
Yeah, this is I don't know. This is not my realm. I'm just reading it.
Yeah.
Pardon my ignorance.
So when you're looking at the directivity of an antenna, you're always comparing it to an ideal antenna, which would be what's called an isotrope that radiates equally in all directions. So that ratio that you see right there, that's generally you express that in DBI gain. So it's the gain relative to an isotropic antenna. There are two conventions, or the Europeans they compare the gain to I believe a dipole. So they have something called DBIC, which you might see sometimes instead of DBI. But essentially you do treat that as a gain. And in the next section of the talks, I'll explain how you can work these gain parameters into your radio calculation, so you can estimate how strong your signal is going to be.
Okay. Follow-up question that from Toby, I think that fits well. Do you think for types of antennas that we're using, do you think the patch antenna is going to be high enough gain for this competition, kind of given what we're trying to do over the expanses we're trying to cover?
Yes. I mean, it depends what distances you want, but even a simple monopole antenna that radiates in all directions, with our higher power tags, we're able to get reading distances of over a mile. So if you use a patch antenna, you can focus that energy and do even better. So I think even with a single patch antenna, that should be more than adequate for what you want.
Okay. Ricky was asking, and Ricky, I see you've entered it a couple times. I can see the question. Are you willing to share your slides? Could we coordinate to get them from you if you're willing to share?
Yeah. These slides. are slides that I just took from one of my classes that I teach at MIT on. So I just took some sets of slides from different radio lectures.
All right.
Yeah. So I
And
don't know where
Aaliyah,
to
you're
post them,
gonna
but I can mail them.
Aaliyah's gonna record the webinar, yeah. Aaliyah,
Okay.
you're gonna record the webinar, so guys can come back and
Yeah.
review the webinar with the slides in it there.
Yeah, so we'll definitely have the webinar up on our YouTube channel, and then Rich, if you can tell us where we can access the slides, we can add that link to the YouTube video.
Okay, sure. I think if I don't know if there's a mailing list or something, but I can
sure,
just make
yeah.
a PDF of the slides and send people the PDF.
Okay,
Yeah,
yeah.
that'd be
So
great.
what we can do is I'll give you a list of everybody that was on this webinar, and we can send it to them.
And we are caught up on questions.
Okay. Maybe we can move on to radio links.
Definitely. Let's do it.
Yeah. All right. So, okay. So, if you actually looked in detail at a radiating antenna, and this one happens to be just from like a simple monopole or dipole antenna. As I mentioned, you have a radiating power and you have other power that doesn't radiate. But when you're building a radio system, and this can be any kind of radio. It could be your cell phone. It could be a ham radio, like a walkie-talkie. But generally, people use power. So people work with in terms of power units, and all the losses and the gains are all expressed in logarithmic units because it makes the math a lot easier. So so you can write if you have a transmitter that's transmitting at a certain power, so PT is a transmitter power, and then the aperture of the receive or transmit antenna are denoted as A, and then G is the gain. So there are expressions you can write that which you see here on the bottom. For those of you who want like a more quantitative equation, you can actually calculate. You can estimate about how big your signal is going to be if you know the different antennas that you're using on the tag and on the reader, and if you know the distance, and if you know your transmit power, you can figure out what the power level is going to be of the signal that you get at the receiver. So as I mentioned, when a signal is going through air, you get what's called path loss. So there's different kinds of loss, and one simple loss is just simply that radio waves spread out. So you have something that's called just spreading loss, and so just like light, if I have a bright light, the further away I am from the light, the less photons are hitting my eye because the light sort of spreads out. Unless it's something focused, like coherent, like a laser that's very coming more as a beam. But typically, a lot of radio waves just spread out. So path loss is generally abbreviated as PL, and it's just simply based on how far you're traveling. So one formula that's very handy to know is this one right here. So even if you know nothing about antennas, you just want to figure out, okay, what frequency am I operating at? In this case, it's 2400 megahertz roughly, 2.4 gigahertz. And how far am I going? So if you know the distance in kilohertz and your frequency, you can figure out how much loss I'm getting, going from point A to point B. So this is a very simple formula that's very handy for radio. So when you're designing a system, we generally think of there's something that we call a link budget. So we want to know, for example, if the receiver that we have or the system that we have is good enough to be able to detect the signals that we want. So you just add up all of these simple parameters like the power of your transmitter, the gain of your transmit antenna, the loss. The loss can be in a cable or a connector. The free space loss, that's what the FS is. That's that previous formula on the previous slide. And then the gain of your receive antenna, and then the loss on your receiver side, loss of your cable, and the cables and connector loss, you can look that up in the data sheet. So if you know, like the higher quality cables are lower loss, but generally it's a few dB of loss is a typical value. And generally you want to have what's called margin. So you want to make sure that you have at least 20 dBm greater power left over. So because if you're operating right on the edge, then things, power levels and signals can vary depending on a dynamic environment. So you know, if your target is moving, or if it starts raining or something like that, like your signal's going to go down. So you generally want to have 20 dB of safety margin when you're designing your system. So yeah, so here I have just a general formula for how you calculate that. Okay, are there any questions on like link budget or estimating that?
Yeah, there are. I'm trying to clarify the question. Actually,
Yeah.
Ronald has a question. Let me read it. Again, this is I kind of understand, but I'm not the expert here. What is frequency, bandwidth, and structure of the interrogation signal from the aircraft? Does that make sense? Is that a good question?
Yeah. So.
Okay.
Um,
Could you clarify what the question is asking? I guess for me, sorry, Ron. You're asking good stuff. I'm just not.
Yeah.
I'm still learning.
Well, there's something that I'm not talking about here, which is I'm just talking about just general RF signals, but I haven't been talking about data rates for the information. So I left out that section of the presentation because you know, I didn't want to go too much into theory. However, those of you who are interested, there's something called Shannon's theorem, and Shannon was a super smart guy who lived, you know, about 50 years ago, and he created a famous equation that lets you calculate what is the maximum data throughput that you can get if you know your signal strength. So, for example, if you do your link budget and you know that, you know, you can calculate like a signal to noise ratio, so you can say, okay, I think, you know, the size of my signal is going to be this. Then his formula lets you calculate how what's the theoretical maximum data rate that you can get through. So for example, Wi-Fi has a good amount of power, and it also has a good amount of bandwidth. So you're able to send a lot of data. Like the data rates of Wi-Fi are pretty high, you know, in the tens of megabits per second, for example. However, in 802.15.4 or Zigbee, which is like the sort of tags that we're looking at here, the bandwidth is very narrow. So because the tags are designed to operate at a very low power and pick up a very weak signal, the filters and the way the radio front end is designed, it's very narrow band. So it's designed to only receive data at a slow rate, and slow is not that slow. Like the Zigbee and 802.15.4, it can go up to, as I mentioned, 250 kilobits per second, which is you know, faster than a lot of the internet phone modems that we had, you know, like 20 years ago. So
Totally.
yeah. So I guess the you know, the answer to the question is that if you look at Shannon's theorem and look into that sort of calculation, you can then figure out the information that you want, how all of this relates to the data. But we're operating well within the data rate of the chip. In other words, we're not limited by the data that we're sending is fairly slow, and we get we're able to get a mile range without much of a problem.
So that makes sense. So you're. Well, let me make sure I heard this. Maybe I guess the intent of the question is Ron's kind of getting down to like what type of information can we be transferring live based on just what sort of throughput we get. So it's you can kind of adjust. Like I guess what
Oh,
where would be important would be things like I guess like video streaming or for navigational responses. I mean, I guess there's a whole bunch of different things that you would use here.
yeah, yeah,
I mean, RFID tag got clearly tracking. That'd be a
right,
big one.
right. So,
And also
so I
interrogating the
realize that
RFID tags. I think that's the
I
main
don't
Targeting.
know.
one.
Yep. Yep.
Yeah,
Hmm.
I don't know the age of the people listening to this talk, but if any of you remember a phone modem and dialing up to the internet, um, so at very slow speeds, typical dial-up speeds, video doesn't work very well. So even with really good compression,
Yep.
so getting text or data packets works totally fine. Audio is kind of okay if you're using good compression, but video, unless the video is really like a small picture, it's this is not the sort of thing that you'd want to use video for.
Yeah. Uh, I'm seeing that.
Yeah.
Not that I wasn't actually thinking that way, but when I see things about bitrate transfer, I'm wondering if others were. Um,
Right. Right. But
So
however,
in the
one of
field,
the yeah.
sorry, in the field we're doing a lot of we're doing data burst, and we do a lot of pretty tricky encoding so that we can do what I call dynamic game viewing, meaning you have a lot of information about the animal you're looking at. It's just a lot of it has to do in how you truncate it using your encoding. So what you can get out of it. We're not streaming video, but we can pass a lot of information based on how you encode it, if that helps anyone.
Yeah. Yeah. So doing one of the big things today is like data compression. So
mhm.
there are fancy ways to compress your data so it doesn't use up as much bandwidth, and there's also error correction, because obviously some of the bits are gonna you might get some errors or lose some bits, and you can recover from that depending on what encoding you use. But one of the things I was going to mention was this frequency band, because it's also used for Wi-Fi. If you did, for example, want to add a camera to your UAV and stream video, you could potentially use similar types of antennas to receive the data stream, because it's the same frequency band. But that's another topic.
Hmm.
Okay.
Okay. Yeah.
If
No,
we
I
can.
think we're good. We're good. I mean, there's stuff.
Okay.
There's some questions, but we can tack them out at the end.
Okay. So this next section is I'm just going to talk about a few real-world effects that you might run into, just to give you some sort of intuition about like the way waves behave. So as I mentioned at the beginning, you have loss as the signal is going through the air. There's a loss going through materials, and there's also loss if you're going through things like foliage, where you're reflecting part of the waves. That's sometimes a word for this is called fading. But so sometimes people aren't sure how to handle or how to think of things like plastics or materials. So depending on the frequency, so at low frequencies being like let's say 10 megahertz, so like a ham radio. So a ham radio signal is low frequency enough that it goes through liquids fine, so it doesn't get too much attenuation going through liquids, or it can go through your hand. However, at high frequencies, that sort of the properties of the air and the properties of the liquid are different enough that you get a lot of reflection. So in fact, most of your power is getting reflected off of the liquid. So if I'm standing in front of a Wi-Fi antenna with a narrow beam, so the beam is pointed, let's say, at my chest, most of the power is just going to be reflected off of my body and not actually even go into my body because of the frequency that I'm at. And you can actually calculate this if you know the dielectric properties or dielectric constant of the human body versus the air, for example. One of the other things to keep in mind is that because radio waves go everywhere, you actually have different signals arriving at the receiver. And this actually is what causes a lot of confusion and problems with RF propagation. So for example, you might be talking to somebody on a cell phone, and this doesn't happen too much now because it's all digital, but in the old days when you had an analog cell phone, you might remember walking around like near a building or at the corner, and the signal would like fade, like it would get noisy all of a sudden, and then the signal goes, it gets strong or gets weaker. And this is because the signals are bouncing off of other objects in your environment, and the signal that's received at the receiver, that arrives at the receiver, is a combination, or it's a sum of the radio waves that go through and the radio waves that got there through other paths that bounced around and eventually got there. And this is what's called multipath. So because the phase of the different signals are different, because the path lengths are different, sometimes the signals will enhance each other, so you'll get a stronger signal, but a lot of the times the signals will actually destructively interfere with each other, so you actually get a cancellation, so the power will be less. So this is why even when you're in an open field, people often ignore that in addition to the sky, you actually have the ground. So the signal actually bounces off the ground, and that gives you multipath right there, because you have a signal that goes straight across through the air, but you have another signal that's bouncing off the ground and getting to the receive end. And those two signals interfere, so you get some noise. Other places that you can get interference are when radio is going through narrow gaps. So, for example, radio waves through a building, or going between big trees, for example. You can also calculate how the propagation works going through, like, over a ridge. So if you have a transmitter and receiver on two sides of a small hill, you can figure out how that signal is going to get over the hill based on the height of the hill and the height of your antenna. But yeah, so these are all different tools you can use. But the main point here is just to keep in mind that the objects around the environment actually have an effect, and at these frequencies that we're working at, 2.4 gigahertz, the signal is really bouncing around most of the objects in our environment. So I'll pause there. I don't know if there's any questions.
There are. They're competition specific. The first one comes from Toby. I found openbeacon.org. Are we able to use this, or is there a specific model or brand that all teams are supposed to use? If we use OpenBeacon, all teams can use the same open source hardware and software. Scott, do you have any comments on are we endorsing certain tags over others?
Not only are we going to endorse them, but we're going to use tags from TagSense. Rich is on here, and that's part of why he's doing it. So we will be using those, but I'm going to go a little bit further. My tech guys and myself are working on some scenarios, and we're going to get a little bit more challenging than just using open stuff. So there will be open items where we'll have open tags, but we'd also like to include some stuff that's encrypted and see if you're able to actually get the keys loaded and go on to encrypted. Because obviously there's no animals that I personally am going to tag that are on an open tag. I think that's pretty clear why. So yeah, we'll do a little bit of both. We're going to do some low power, some high power, some open, and some encrypted, and we'll be passing that along as we go. But obviously your tags are going to be the same. It's going to be actually in how you program the reader when you get into the encryption part.
Okay. I think
Yeah.
looking at the time check, guys. We're at 53 after. Is it okay if we, Rich, are you okay to go a little over? I think you still have some content that's pretty critical here.
Sure. Yeah.
Do you have a, yeah.
This is the last section. I just have a few
Okay.
slides on the tag sense hardware specifically, and then we can have another separate follow-on webinar if people need more specific information.
Okay. Thanks for the offer. We might consider doing that, maybe in like a month or so, because people are still building it. Thank you for the offer. I think we will probably end up picking
Right.
up on that. Yeah.
Okay. All right. So I'll go ahead and move on this. So the tag that we have a few different form factors, but this is the most popular one. This is the low power tag, 1 milliwatt, and this is what it looks like. And I should mention that there is an open standard called IEEE 802.15.4, and there are chipsets. So we happen to use chipsets from Texas Instruments, formerly known as Chipcon. So Chipcon is a company from I think Norway that got bought by Texas Instruments about 5 or 6 years ago, and they're a great RF company, and a lot of the Zigbee chips or 802.15.4 chips use or applications use their chipset, and the protocol is more or less built into the chip. So what we do is we have modified the protocol, the higher level protocol, a little bit to support sensors and programmability. But if so, I think for the competition, it's probably simpler to just work with the off-the-shelf protocol. But what some we often sell tags to a lot of students and schools, and what some students have done is they've loaded their own firmware onto our hardware. So if you know the pinout, you can write your own firmware, and you could write your own protocol or whatever you want. But because that requires fairly advanced knowledge of the 802.15.4 protocol and what they call protocol stack. It's probably simplest for the challenge to just work with the off-the-shelf protocol, unless but we're happy to support people who are advanced and want to play with writing their own firmware for the tags. It's sort of up to you guys, but we're flexible. Okay, so this tag is a 1 milliwatt class tag. As you can see from the middle picture there, there's a header which allows you to connect about 4 or 5 different analog sensors. There's also some pins that let you connect digital information, so you can connect the tag to another microcontroller if you wanted to. Some people have connected a GPS unit to our tag. So there's a lot of things you can do with it.
Which microcontrollers work best with them? Do you have?
Sure. So
I mean, do you endorse like kind of the typical ones like the Arduino or the Raspberry Pi? I mean, what are their?
Yeah. So the microcontroller that we use on our tag is the Atmega 328P, which is a standard microcontroller used in most Arduinos.
Okay.
I believe our reader uses the Xmega, which is a more advanced 8-bit microcontroller, and there are a few Arduinos that use a more advanced, but we use pretty much the same microcontroller family that is found in the Arduinos, made by Atmel.
Okay. Bharat, you asked that question. Let me know if that didn't answer your question. Yeah, I imagine Rich will probably be hitching up with some ideas there in the follow-up.
Right.
That's
So
thanks.
If you look at the if you go to the Texas, for those of you who are more interested in the details of the radios and the chipsets, you can go to the TI website and look up the older chip that is used in the low power one is the CC2420, and then our higher power tag uses the CC2520, which is the newer version, which has slightly more power. So if you want to read the details, you can look up those specific chips. And this is where, on this next slide, you can see the higher power version of our chip. Not only do we use the 2520 chip, but we also add the 2591, that's the chip part, CC2591 amplifier, which gives you a boost of the transmit power, but it also amplifies the receive signal. So it helps you to receive weak signals from like if you're sending a command to your tag. And this is what it looks like. Now the downside of the higher power tag is that now you're dealing with sort of Wi-Fi sort of class powers, hundreds of milliwatts, for example. And in this case, the size of the tag is really dominated by the battery size. So you can see on the right is sort of the bare bones tag, and you can see the 3 chips there. There's a 4th thing that looks like a chip, but that's actually just a crystal. So there's a microcontroller, the CC2520, and then the amplifier chip. Those are the 3 chips that are used. And it also has an onboard regulator, so you can feed it a higher voltage, and it gets regulated down to 3 volts. Now on the left, you see one example of a package tag which holds 2 AA batteries. But we've done some smaller versions that, if any of you want to package your own batteries or use a smaller case, you can just buy the raw tag and play around with it, whatever battery you want. Now, on the reader side, our general reader board looks like this, and it essentially looks the same as the tag board that's on the right, but it also has this additional circuitry, because we also sell this for use with USB, so you can connect if anybody's using like a Raspberry Pi or some other computer, you can connect this reader via USB to an external computer, and it also has this header that's in that sort of IDC10 connector on the upper left, and that has full RS-232 plus minus 8 volt signals that lets you connect to serial ports if anybody still uses kind of the old serial port RS-232 signals. The way you connect to this, so if you're connecting a microcontroller, so the power for the board goes through that header up on top. The 2 pins on the right is power and ground, and the regulator can take roughly anywhere from 5 to 9 volts, and it gets, or maybe like 4 to 9 volts, and it gets regulated down to 3.3. And then talking to the chip, if you want to plug into your own circuit board, there's that 4-pin header, and you can see it has 3.3 volts, ground, TX, and RX. So you can actually, if you have a small microcontroller, you can actually power it from the reader, or you can go vice versa. But the main thing here, so the biggest mistake that most people make when they're using Arduinos is they try to use a 5-volt Arduino to talk to a 3-volt board, and then they can't figure out why the communications is not working. And it's because you have to make sure that you're using a 3-volt Arduino and not a 5-volt Arduino. And then we also can load the reader firmware onto the same tag footprint. So this one has a connector for an external antenna, but this one's special order. So as I mentioned, we generally just sell the reader in this sort of form factor, which includes the USB portion as well. In terms of software, well, let me just show this slide first. The data that, if you turn on your reader and there's a tag or several tags transmitting, you'll get data packets that look like this. So the data is all in hex. So hopefully most of you know or are familiar with hexadecimal notation, base 16. So 1 byte is basically 2 characters, also known as 2 nibbles. So here's an example of how each packet can be parsed. The data, the packet size is variable to save bandwidth. So if you want more details on how to parse a packet, you can download the datasheet from our website for the tag protocol. But here's an example. So as you can see, in this particular example, we have 4 sensors connected to the tag, and we're receiving this data packet. So the data packet includes the ID of the tag. It also includes the battery voltage of the tag, so you can monitor how your tag is doing. It also includes the signal strength. So the last byte of the tag packet, which in this case happens to be FE, that is the signal strength. And it also includes the 4 sensor values. So the analog to digital converters that are built into the chip and built into the tag is 10 bits. So you get a 10-bit value, 0 to 1024 essentially. If you want to connect any analog sensors. The tags made by TagSense have a huge number of functions, which I won't get into here, which I invite you to look at the data sheet. But there are a variety of configurations that you can use to program the tag. You can vary how often the tag transmits. You can you can set the tag to transmit only when it's triggered by an external sensor. So for example, you can attach a vibration sensor so that if there's a small vibration, it'll trigger the tag to transmit a data packet, for example. So there's a lot of things you can do. It also has a real-time clock. Some of our customers use it for data logging. You can also program different behavior at different times of the day. So there's a lot of things you can do. We also have software. So for those of you who don't want to mess with the low-level data and looking at the text or the hex values, you could just get our software, and we'll have to. This is something that I will need to discuss directly with the UAV challenge organizers, but I might make a version of the software available for free for all the teams. We generally provide the software with the source code for the software as part of our kit, so for people who are writing their own software. But if I remove the source code, if you just want the executable software, I can make that available for free. And it's a nice little tool because it allows you to automatically parse the data that's coming in. Here's an example of the parsing window. And so it tells you when you intercept the tag packet coming in from a particular tag, it'll tell you what the sensor values are and whether it's analog or digital, for example. There's also another window that lets you configure the tag, and there's a variety of tabs. But this particular tab lets, for example, you can see you can set how often it transmits. You can set the transmit power level, and you can also change the ID of the tag. Yeah, so if you want more information, you can look at our website. We also have an online store, but I believe the most up-to-date data sheets are probably on the online store, so you can download the PDF files from there. We also have a small example of, we have a video on YouTube, and this one happens to be a video of an Ethernet reader. So we also make readers that can be connected on your local network through Ethernet. But you can ignore the Ethernet part, but just look at, it just shows you how, what the data packets look like. And that's our link for the active tags page on our store. So I think that's it. I'll take some questions, and then we can wrap up.
Oh, sorry. I think I got a delay there. There are questions. The second follow-up is some more clarifying questions. This set of various components you showed there, is this going to be one big endorsed kit, or are we just kind of going with the RFID only? I guess maybe this question is more for Scott. Which of this hardware is going to be standard, and which stuff are we still flexible to change around on for the teams?
Is it
yeah, like I said.
Yeah, go ahead.
No, go ahead, Rich.
I was just going to say that the readers that TagSense make, they're essentially a pass-through. So they pass along the data that's coming in, the data packets that are coming in from the tag. So they could be adapted to work with anybody else's tag that uses the 802.15.4, or if anybody else is making tags that is using the ChipCon chipset, our reader can receive those, and then you get those data packets instead. But obviously, you know, our software only works if you're talking to our own tag.
Yeah, clearly. I think I understand that. Michael Robbins, you asked that question specifically. Do you feel like you understand kind of how the nuance there? If not, we'll follow up with you directly on that. Go ahead.
Yeah, and we can we'll throw out a handful of South African-made RFID tags as well that are open, and we'll allow people to interrogate those as well. So you know, we'll make sure it's pretty standard. Everyone will know what software is being used, and the idea is to promote innovation. So if people can design their own reader and their own antennas, that's the exciting part of it. So more power to you.
Yeah, clearly, definitely. There's areas where if you have the standard stuff, I mean, if you already have things that are working in the park, I mean, I think definitely among my team, if you guys kind of had a play that you already endorsed, I know that would help us out, because we're definitely still trying to navigate and learn this stuff. Yeah, thanks. That's helpful. Nicola has a question about the issues of interference. Do we know, are we receiving signals from more than one tag? I guess if there's more than one Rhino, clearly there would be. But where do you see the most areas where we would see interference, and then how do we deal with that? How do you?
Yeah, no, that's a good question. For this particular scenario, we would just be using what we call an ad hoc network with a star topology, and the reader is able to receive data from multiple tags, and the density of the tags, in other words, well, at least I'm assuming that the number of tags is not going to be that high. But if you get into like hundreds of tags, then we actually use a different version of firmware, which is time multiplex, where you have a network where each tag has a particular time slice that it talks, and that's used. So that's another variant of the 802.15.4 protocol, which is called like a beacon-based network. However, for this particular application, and the easiest configuration to use is not to use time division multiplex, and just have it be ad hoc. So it is possible that two tags can transmit at the same time, but the tags are programmed with CSMA, which stands for Carrier Sense Multiple Access, and with exponential backoff. So when a tag gets ready, when a tag wakes up, so let's say it's programmed to wake up every 10 seconds. So when it wakes up, it'll first listen to see if there's anybody else talking at the same time. If there is another tag talking, it'll wait a fraction of a second and then try again. And you know, that's sort of how it works. And it's automated. Yeah, so this standard version of the firmware is designed to be as easy to use as possible, and it doesn't require like a mesh network or a complicated multi-hop topology that like we might see like in Zigbee, for example. So this designed for an ad hoc network where tags are coming in and out all the time, and you can minimize the amount of coordination and communication between the different pieces of the network.
Okay. Well, I think I don't see any outstanding questions that are in my list here. I'm sorry, guys, if I missed any. I think we're ready to kind of start drawing to a close. Princess Lee or Scott, did you guys have any kind of general announcements or things you wanted to say before we
I
bring
think
it
there's
to an
there
end?
I think there's a question from Toby which says, so is there a standard kit that we can buy? I think we're trying.
Oh yeah, reply back
Yeah.
to that.
Oh,
Yeah.
you did. Okay.
Um,
So what
well,
we're
let me
gonna
take it.
do?
Oh, go
Sorry.
ahead.
Oh,
No,
sorry. I was
go.
gonna
You
say
got
we're
it.
gonna work with Rich and then LB in South Africa, and we'll probably compile something that is gonna be low cost. Uh, and the primary thing for the teams is to be able to interrogate the tags. So what we're going to do is we're going to work together and put a package together that you guys can either purchase. We'll probably have some things that we can make available for free, but
Okay.
that's something I'll have to work out with Rich, and then LB will have to work that out on his end in South Africa, and give us about 2 weeks to 3 weeks to put this together, only because I think we're just also trying to coordinate what exactly will be available at the final competition. So we don't want to give you something that you're not going to be dealing with once you do get there as well. So
Yeah.
that's why we'll probably need at least two to 3 weeks to figure all of that out, and we'll have that available for you, Toby, and the rest of the teams. But I do want to make an announcement that the critical design review is going to be posted and available by the end of the day today, Eastern time, of course. Uh, so for some of you, it will be really, really late night. But I did want to clarify that the critical design review will be available on our website later today.
Cool.
Um,
That's awesome.
if
That'll
I
be
could
super
make
helpful.
I just wanted to make a comment on the ordering or the cost that active tags. A lot of people think that passive tags are a lot cheaper. However, if you want to if you're interested in buying a high performance long range passive tag reader, those readers cost a couple $1,000s, even though the tags cost 50 cents or 20 cents. The reader itself is very large and generally costs a lot of money. So active tags, even though the tag cost is on the order of 50, $60, the readers are a couple $100s. So it's the difference in cost between the tag and the reader is more similar. And in terms of ordering, it, as I mentioned earlier regarding the software, rather than ordering the kit, you like teams can or whoever's going to order, you can just order tags and readers individually. You don't have to buy a whole kit. And I will, as I mentioned, I'll work out an arrangement so that you guys can get the software for free that you can use to configure and read the data packets from your tags.
Excellent.
All right, friends. We are over time, and but I know that we're going to continue to have questions on this thing. So Rich and Scott and everyone else. I mean, I know that we'll want to do more on this. So I will. Let's get back together soon, maybe in the next month or so, and continue on this stuff. So thank you, Rich, so much for running us through this stuff. I know that this is an area that I personally need to learn more about, and I really appreciate you taking the time to share your expertise with us. And so whether you're new like me, or in this case, we have some very seasoned people that are very talented in doing some stuff on their teams. I know this is a really good use of time, and it's been a point of interest for quite some time among all of us. So thank you for being here. Scott, likewise, thank you for being here and clarifying on your end, across the globe in my case. And Priscilla, you and I, we will see everyone on the next webinar. Have a great day, guys.
All right.
All right.
Take care.
Thank you.
Okay,
All right.
take care,
Thanks,
everyone.
Rich.
Bye.
Bye.
All right. Bye-bye.